Shri Gurubhyo Namaha. Welcome to our online learning initiative Ekalaiva. We are going to discuss mutual induction. First, let us see what is mutual induction. Actually, it is the phenomenon of production of induced EMF in one coil due to the varying current in the neighboring coil. Okay, now let us consider two coils, that is primary coil and secondary coil. Let us consider this is the primary coil. This primary coil which is connected to battery, and we are going to connect tap key. So this is the primary coil. Let us consider P1, P2, and this is the battery, positive, negative, and tap key. And we are going to place one more coil very close to the primary coil. And we are going to connect galvanometer here. So let us consider this is our secondary coil. So we connected primary coil with battery and key, and we placed one more coil, that is secondary coil, on this secondary coil which is connected with galvanometer. Okay. Now the two circuits are said to be coupled circuits. Okay, we can also say that coupled circuits. Okay, so with the help of this we are going to see what is mutual induction. So now here when the tap key is pressed, we are going to press this tap key. What will happen? The pointer of the galvanometer, which gives a sudden deflection in one direction. For example, let it be in the left direction. Now, when you release the key, once again what will happen? The galvanometer will give deflection to the right side. So when you press the key, you can see the deflection in the galvanometer towards left. But when you release the key, you can see the deflection in the galvanometer to the right side. So what is happening here? Now I will give you complete explanation. Actually, when we press the key, the current in the primary coil which begins to increase from 0 to maximum. So during the growth of the current, that is from 0 to maximum, the magnetic flux linked with the primary begins to increase. So whenever the current increases from 0 to maximum, the magnetic flux also will increase. Okay, since the secondary coil which is placed very close to the primary, the magnetic flux linked with the secondary also begins to increase. This sets up an induced current in the secondary. But now we are going to recall very important law here, children, Lenz's law. So according to Lenz's law, the direction of the induced current in the secondary, which will oppose the growth of the battery current in the primary. Okay, so the deflection of the galvanometer is due to the induced current in the secondary. Okay, so this is very, very important here, children. Now, let's see what will happen when the key is released. So when the key is released, what will happen? The current in the primary coil begins to decrease from maximum to 0. So again what will happen? The magnetic flux linked with the primary as well as the magnetic flux linked with the secondary begins to decrease. So due to the decrease of magnetic flux linked with the secondary, an induced current is once again set up in the secondary. So again, according to Lenz's law, the direction of the induced current, it should oppose the decay of current in the primary. Okay, that is decay of battery current in the primary. So this is possible only if the induced current flows in the same direction as the battery current in the primary. So this is why, because of this only, the galvanometer gives deflection to the right at the time of break of the circuit. So when the key is pressed, the deflection in the galvanometer towards left means when the key is released, the galvanometer will give the deflection in the right side. Okay, so this phenomenon is known as mutual induction. So once again, I can say that actually this mutual induction is a property of two coils by virtue of which each opposes any change in the current flowing in the other by developing an induced EMF. Okay, now let's see what is mutual inductance or coefficient of mutual inductance. Okay, so I'm going to discuss about coefficient of mutual induction. Coefficient of mutual induction, or we can also say mutual inductance. Okay, so we know that what is flux? Magnetic flux is phi B. Okay, so now let us consider phi B be the magnetic flux linked with the secondary coil. Okay, phi be the magnetic flux linked with the secondary coil when current I flows through the primary coil. Okay, so we know that magnetic flux is directly proportional to I, or else we can also say that to remove this proportionality, constant of proportionality is capital M here. What is this capital M? This is nothing but the mutual inductance or coefficient of mutual induction. Okay, now let us assume if I is equal to 1 ampere, then we can say that mutual induction M is equal to phi. Okay, so we can say that the mutual inductance of two coils is numerically equal to the magnetic flux linked with one coil when a unit current flows through the neighboring coil. Okay, now I am going to differentiate this expression. So when I differentiate this, what will I get, children? So let us take d phi by dt is equal to, we cannot differentiate m because it is a constant. So we can differentiate only I. Okay, so di by dt. But already we know that what is induced EMF? Induced EMF is equal to minus d phi by dt. So I am going to substitute induced EMF is equal to this, instead of this d phi by dt minus m di by dt. Okay. If di by dt is equal to 1, then you can say that numerically equal to, that is mutual induction is numerically equal to this. So we have to numerically is very important here, children. Okay. So the mutual inductance of the two coils is equal to the induced EMF set up in one coil when the rate of change of current in the other coil is unity. Okay, so this is very important. And now let's see what is the SI unit of mutual inductance. Actually, the SI unit of unit of mutual inductance is Henry. Now let's see factors on which mutual inductance depends. The value of mutual inductance depends on number of turns. So it depends on number of turns of the coils, and it also depends on separation between the two coils, separation between the two coils, then it depends on geometrical shape and size, then the fourth factor, which is very important, angular orientation between the two coils. Okay, so I'll write here orientation. So angular orientation between the coils. So what are the factors on which mutual inductance depends? It depends on number of turns of the coils. It depends on relative separation between the two coils, then shape and size. Then the fourth one is angular orientation between the coils. Now, let's consider the first case here, children. If one coil is perpendicular to the other, then mutual inductance is minimum. So here, mutual inductance is minimum. Okay. Now let's consider this case. When the entire flux due to the primary is linked with the secondary, then the mutual inductance is maximum. Here, mutual inductance is maximum. Okay. So here the mutual inductance is minimum. Here the mutual inductance is maximum. And we can also say that this mutual inductance can be increased mu times when the two coils are closely wound on an iron core whose permeability is mu. Okay. So now let's see the third case. Here, if the two coils are arranged like this, then the value of a mutual inductance here in this case, the value of mutual inductance is intermediate. Okay. So here is the case. You can say that the value is intermediate. intermediate value. Okay, so if the two coils, or that is if one is perpendicular to the other, then mutual inductance is minimum. If it is arranged like this, then it is maximum. If the two coils are like this arrangement, then the mutual inductance has intermediate value. Okay, so I can also write that mutual inductance has intermediate value. Okay, so this is very, very, very important, children. Okay, thank you.